Module 4.2, Theoretical Foundations of Coarse Graining. Let's start with an overview of coarse graining methods. When we say coarse graining, typically what it implies is reduction of degrees of freedom. So we aggregate atoms into beads, and we try to minimize the number of interacting elements that might simplify the computational model and also make it very efficient. However, we do want to conserve key properties to ensure that the important thermodynamic and structural properties are preserved despite the reduction of the resolution. So for this, the typical procedure is you take a coarse graining potential or force field, which is a function of all atom force field, that is Ri here is the position of the coarse graining beads, and Rj is the small rj are the position of atoms. Then we try to define a mapping function chi I, which basically maps it from atoms to beads. And there are some other mathematical deductions. But the idea is this capital Ri and small ri, how to establish relationship between them. That is the key important part of the coarse graining, which is quite non-trivial. So there are different approaches for accomplishing coarse graining models. So it could be top-down approach or bottom-up approach. So in top-down approach, you're going to take real experimental observation of thermodynamic or macroscopic properties and try to fit a coarse graining model. Or you can take atomistic models, and from there, you can try to match the coarse graining model that you are trying to fit to. So simulating coarse graining model requires coarse graining force field. So it's in that way very similar to molecular dynamics that we learned in the previous module. However, developing coarse graining force field is quite non-trivial, and this is why machine learning force field in future might be helpful. So similar to the typical molecular dynamic force field, this also requires parameterization, and we talked about it. It could be top-down or bottom-up approach, and we want to simplify interactions. And there are many types of coarse graining models. One of the most popular one is FENE, or finite extensible nonlinear elastic model. We're going to talk about that in a few seconds. Before we go into that, I want to point out there are many softwares out there to accomplish coarse graining modeling. So one of the most famous one is Martini, and there are variation of Martini software. There's also other Vodka and OpenMM coarse graining, and many other softwares are there. In our tutorial, we might be focusing on Martini and GROMACS a little bit. So as I said, there are in Martini itself, there are different versions and there are different tools for setting up calculations, building topology, and so on. And it has been highly successful in the area of macromolecular design. So as we said, there are different types of coarse graining force field. So one of the most popular one is the FENE, finite extensible nonlinear elastic model. And in that, it is used to model the bond interaction within polymer chains, and it prevents it from stretching beyond physical limits. So this was first proposed by Kramer and Grest, and they successfully showed this. It might work to match experiments, so which was quite successful. And you can imagine it to be a bonding interaction, U bond, to be a combination of FENE bond and Lennard-Jones bonds. We learned about the Lennard-Jones bond already, the 612 potential, but here we are considering another term called FENE term, which will try to capture the bead interaction as well. There are also other force fields such as Martini. So Martini utilizes a 4-to-1, that is 4 atoms to 1 bead mapping, and it's widely used for biomolecular system. There are others which we'll not touch upon during tutorial, but just good to know that like unrest force field, Sierra force field, and DPD, or dissipative particle dynamics, in which a particle-based simulation method that can conserve momentum. So remember, we do want to follow the basic laws of physics, conservation of momentum and so on, and use it for hydrodynamic behavior of macromolecular simulations. So how do you select a force field? So it depends whether you are simulating the system is like biological system or polymeric system and specific properties. So you might be interested in specific heat or radial distribution function and so on. So based on that, you might want to choose particular force field. It also depends what kind of computational resources you have in your lab or laboratory. So there are several challenges of using coarse graining force field. So first of all, when we go from fully atomistic to coarse graining domain, we lose a lot of information. So this could be important for capturing certain phenomenon. So it comes with a price. Parameterization, as we mentioned, it could be quite difficult and non-trivial, sometimes very manual to fit such coarse graining force field. And this is why there have been several research work to use machine learning to automate this process. Transferability, so we talked about that. It's very, if you fit the model to a particular system, such as a particular type of protein or DNA, it may not be applicable for other system. And of course, scale bridging, as we said, we're trying to map from experiment to coarse graining or at fully atomistic to coarse graining. And it can be quite difficult to scale the bridge between them. And there are several challenges because we still want to follow the conservation laws, conservation of energy, and so on.